Chapter 4 with that. So in chapter 3 we were starting to learn about alkanes, right? So these are just carbon-carbon single bonds. With that. So now, right, but they were all, but in chapter 3, right, so the carbon chains were all aligned. So now we're going to talk about the situation where, the ends sort of meet up, and so they're bonded together, right, so to form a ring, right, so with that. And so those, we call those cyclic alkanes, right? So it doesn't matter the size, we're going to all call these a ring. So even if it's, right, so these three are all bonded in a ring. So right, that 4, 5, 6. Doesn't matter, the first and last ones are tied together, stuff like that. So first thing we always do with new compounds, right? We talk about the naming. And so we're going to go through the same 4 steps we've always done, right? So first thing is, right, we always have to find that main chain. Right? So the main chain, right? Before, right, it was the longest carbon chain. It's still the same. That rule still applies. Stuff like that. However, you have to ask yourself which is longer, right? The ring or the chain that extends away from it. Most of the time, it's going to be the ring, right? And you consider those separately, the ring and the longest straight chain. How about that? Most of the time, it's the ring. If it is going to be the ring, instead of to indicate that, right, it's cyclic, we actually put cyclo in front of it. So hexane would be 6 in a row, straight. A cyclohexane would be 6 carbons in a ring, stuff like that. So that's going to be the main chain. Now, the only caveat is if the straight chain is longer than the ring is around, that straight chain is going to be the right. So the straight chain is going to be the main chain, stuff like that. It has to be actually longer. Most times, it's not going to be the case, but it comes up every once in a while. So, okay, so from there, alkyl groups just like normal, like that. Now the numbering is the difficult part. With the numbering, the problem is where is carbon 1, right? Before, right, for the straight chains, it would be the left or right end, right? But for here, since it's a ring, where do you start from? Where is carbon 1? So the trick usually, right, we still need the lowest number set, but what the best way to find it is to assume where a side group attaches, assume that that's carbon 1, and then go either clockwise or counterclockwise towards its nearest neighbor. And you do that for each side chain. Right? So you go to the next side chain, you assume that's hanging off of carbon 1, and then go clockwise, counterclockwise towards the next one. So if you have three things hanging off, you should probably do the numbering 3 times and see which you add them up, figure out which one. But that now. The problem is if there is a tie for the lowest number, there's no other way to resolve it. The thing to do is the first alphabetically gets the 1, basically, or gets the lowest number set. It's usually going to be the number 1, and then you go from there. So they had to figure out a way to break the tie. That's how they decided to do it, right? And then you put the names as just like the straight chain, right? So you put the alkyl group here, right? Remember the di, tri, whatever. Doesn't matter. So if your cyclo group happens to be a side chain, it's just like you don't consider that, right? So propane, right? So the methyl comes before cyclopropane because it's the propane that's the important part. So you just put it as normal, right? So okay, so we're gonna do some examples, right? Okay, so here's the first one. Right, so here we go. So we have our six carbons here, right? We have 1 up, 1 over, right? 1 down. Okay, so here we go. So the longest alkyl chain, right, is 1, 2. Yeah, this one's 2, this one's 1, but the ring here is 6 around. 1, 2, 3, 4, 5, 6. Now you either do the ring or you do the side chain. You don't do both, right? So you're either gonna do the ring or you're gonna do the straight chain. Not both. You don't go 1, 2, 3, 4. You don't go straight chain and into the ring. It's either one or the other, right? So this right here is going to be our main chain here. Okay, so these are the carbons of the main chain, right? So it's 6 carbons long, right? So that would be hexane, right? However, since it's a cyclo group, since it's a ring, it'd be a cyclohexane. Okay. Okay, so what else do we have? So for side chains, right, we have this one here, and that one, right? So we have a methyl, right? Because it's 1 carbon long. We have this one here. It's 2 carbons long. Methyl. Right? You don't count the ring because those carbons there are included in the cyclohexanes. We've already named them. It's just these two, this one, these two, and this one have not been named, so we have to put that in the name. Okay, so how do we do this? Okay, so you start it. Just pick one. So we're gonna say this one. So we're gonna go 1. You go towards the nearest neighbor, right? So you could either go clockwise or counterclockwise, but the nearest neighbor is clockwise. So we're gonna keep going around. 1, 2, 3, 4, 5, 6. Right? So you have 1, 2, 4. Okay, so, but the problem is, what if carbon 1 is there, right? So now we say, okay, let's say carbon 1 is here, right? Then you go towards the nearest neighbor. In this case, it would be here, right? So we're going to go counterclockwise around. So 1, 2, 3, 4, 5, 6, right? So this methyl would be a 2, the ethyl would be a 1, and with the blue numberings, this methyl is at 5, right? And now, last one is, well, what if this one was 1? So we go 1, 2, 3, right? Because this is the nearest neighbor here, as opposed to all the way around there. So we're going to go counterclockwise again. So 1, 2, 3, 4, 5, 6. Right? So now this is at 1, 3, 4. Notice that we're going to start. We do 1, 1, 1. Right? So one set where this is number 1, another set where this is number 1, another set where this is number 1. And we'll go to the nearest neighbor. Now I'm going to add them all up. So 7, 2, 7, 8, 7, 8. Okay, so since this is the lowest sum, we're going to pick this one here, right? So here we go. So we have our numbering. So now we need to figure out the name, right? So which comes first? Ethyl or methyl? Ethyl comes first. So we're going to go. We have to list that one first. So it's 2-ethyl, right? And then we have 2 methyls, right? So we're going to have a dimethyl. Right? So we have 2 methyl groups, right? One at carbon 1, one at carbon 4, right? So there's all our side chains, and then we put the main chain at the end, so cyclohexane. So it's 2-ethyl, 1,4-dimethyl, cyclohexane. There you go. So the next one is this one here. So, okay, so here we go. So we have a ring and we have a straight chain, right? So again, you don't, right? So you either consider this or you consider the main chain. You don't go into the chain, or you don't go into the ring, right? So here we go. So this one is 1, 2, 3, 4, 5 around, right? But this one here, if you go 1, 2, 3, 4, 5, 6, right? So I can make a longer chain like this. Now, you could technically go 1, 2, 3, 4, 5, 6, but it's easier to name it like this, have these two be separate side chains, than name this one giant side chain. Alright, so technically you could do it, but it's a much better, it's going to be much easier to do these 2 separate side chains as opposed to this one here. Okay, so this is actually our main chain here, because this is 5, and our main chain is 6, or our straight chain is 6 long. So since it's larger than the ring, we're going to say that this is the main chain. Okay, so here we have a C5, right, which is 2, 3, 4, oh, excuse me, C6, 1, 2, 3, 4, 5, 6, so that'd be hexane, right? It's a straight chain, so no cyclo. Okay, so now, right, so now for the side chains, right, we have that guy, and we have this one, right, so we have a methyl group, right? But how do we name this, right? Well, if it was just a regular, right, so if it was just a regular alkane, it would be cyclopentane, right? Right? But just like any other side chain, right, we remove the A and E to say it's a side chain and replace it with YL, so it'll be cyclopentyl. Okay, so it works no differently than methyl, right? It just so happens to have the cyclo in front of it. So, okay, so we have to figure out the numbering, right? So we're going to do from this end, so we're going to do 1, 2, 3, 4, 5, 6, right? So cyclopentals at 1, methyls at 2, right? Or we could do from this side 1, 2, 3, 4, 5, 6, right? So here cyclopentals at 6, this one's at 5, right? So add them up, so it's 3 versus 11, right? So so this is the name. All right, we want to do the smallest number set. So right, so wherever this adds up lowest, we go here, right? So here we go. So be careful, right? So we have to put in our sidechain alphabetical order. It's not methyl versus cyclopentyl. It's really just methyl versus pentyl. Okay, so methyl comes first. So it's 2 methyl, 1 cyclopentyl hexane. There we go. All right, we have a straight chain that's 6 long. 1, 2, 3, 4, 5, 6. We have a methyl group hanging off of carbon 2, and we have a cyclopentyl group hanging off of carbon 1. So there we go. Okay, so last example, right? So here we go. So, all right. Okay, so our ring here is 4. 1, 2, 3, 4, right? The longest straight chain is either 1 or 2, right? So the ring is the largest, larger than any of the straight chains. So that's going to be considered the main chain. So it's 4 around, right? So normally that'd be butane, right? But we're going to say, because to indicate that it's a ring, we're going to say it's cyclobutane. Okay, right? So here, yep. So this is our main chain there. Okay, so now what side chains do we have? This one and that one, right? So we have a methyl and an ethyl. Okay, so here we go. So if we said, okay, this is going to be number 1, right? So we go towards the nearest neighbor, so that would be, make it goes clockwise. So this would be 2, 3, 4, right? So this would be 1, 2, right? But instead, let's say this is 1, and then we go towards our nearest neighbor, so that would mean, so it's counterclockwise, so it's 1, 2, 3, 4, right? So it's 1, 2. Okay, so you add them up, and it's a tie. And there's no other way that we can name this, right? So you could do this, you could do other namings, but these are going to be the two lowest ones, and we can't figure out another way to do this. Okay, so to break the tie, you say, okay, which one's first alphabetically, ethyl or methyl? It's ethyl, so this is going to be, this one gets the number 1. Okay, so like that. So it becomes, because this is first alphabetically, it gets the 1. So it becomes 1 ethyl, 2 methyl, right? Cyclobutane. There we go. It's only if there's no other way you can do it. If you can find something, right? So there would be any way that I could get a 2 here. If there was a 2, if there's a way that I could get a 2 here, I'd pick that one. But otherwise, there's nothing smaller than a 3. So you're stuck with this tie. So you got to break it with the alphabetical rules. Like that, so there you go. Okay, so cis-trans isomerization and cycloalkanes. Okay, so you have to think about these cycloalkanes. Okay, so as right, so normally carbon-carbon bonds can freely rotate, right? So if you have a carbon-carbon bond like this, right, they can freely rotate, no problem, right? But the problem is if you have a cyclo, so in this case a cyclopentane, right? You can't rotate. You can rotate a little bit, right? But you can't really do the whole thing, right? So you can get about to there, and then unless you break the bond, unless you break your model set, it's not going to happen, right? So it's going to wiggle around a little bit, but it's kind of fixed. It's basically fixed in space. Okay, so in some ways we can say that there's so because it's sort of fixed, we can actually say that there's sort of a top and a bottom phase to these things. There's 2 phases to this. Okay, now, so since they have faces, right, it makes a difference if, say, if you had 2 groups here, one's up, right, both of them are on the top phase, or if one's up, one's down. Okay, one's on the bottom phase. One's up, one's down. Okay, it actually makes a difference, right? So if they are on the same side, right? So they're both up or they're both down, right? So in this case, they're either both up, right, or both down. That's called cis, right? So like a C, right? Cis, right? So C. Okay. Now, if one up and one down, right? So one down, one up. That's called trans. Okay, and they'll have different properties. So if you look at this, right? So cis 1,3 cyclopentane, the boiling point's 37. The trans version has a slightly lower boiling point, right? So they are different. Okay, so about that. So it's not just something spurious. Okay, so this one actually looks rather flat, but that's actually not how it works. So that's originally what they thought. It was that everything was flat. It took them a long time to realize that in fact they're not, and because one of the reasons why I thought it was flat was because just simple geometry, right? So they thought, okay, if the rings were flat, right, you look at the bond angles, okay, so if you just draw a simple triangle here, right, so tetrahedron wants to be 109 degrees, right, so that's the easiest, that's the least stressful it is on it, right, so, but cyclopentane, right, so it's 60 degrees, so bond, shifting that bond in is really stressful. That's why it's really tough to make a cyclopentane with your model kit, right? Because you have to really bend it. Hopefully, you don't break it, right? So as you get larger, right, you should get much less angle strain, right? So you don't have to bend the model those bonds out of the 199 degrees that it wants, right? So in 100 cyclopentane should be the best. Right? It's only 1 degree off, right? So the angle, if everything's flat, it's 108 degrees, right? It wants to be 109. Not too bad, too shabby. And cyclohexane should be a little bit worse, right? Because you're 11 degrees outside, a little bit farther away, right? So this should be the most stable, followed by this, and then that, and then that. Okay, just looking at the angle strain. But what you found from the lab measurements is actually these two are reversed. These two are still terrible. These two things are really these things are unstable. These two rings, but in fact, what happened was the cyclohexane was the more stable of these two. Okay, and so it really took a long time to figure out why. Okay, and actually, there's 3 different types of strains, right? So we've already been introduced to angle strain, right? If you have to bend the bond outside of the angle that it really wants to be in, so in this case 109 degrees, that's called angle strain. Torsional strain is whenever you have to twist, right? So if you have to twist it to get out of a bad situation, it applies torsional strain, so you put a torque on it. So about that. So that's a torsional strain. If things are pointed towards each other, sometimes they'll torque a little bit, provide some torsion. That'll provide some torsional strain. Okay. The last one we've already been introduced to was Steric Strain, right? So remember the Newman projections, right? So if you had CH3, right, that's going to be a Steric Strain, right? So, right, if you have, right? So we talked about this last chapter, right? So if these two methyl groups are sitting right on top of each other, right, they're going to be clashing, right? They're going to be knocking heads, right? So that's going to be steric strains. So steric strains are 2 groups hitting each other, so like that. So these are the different types of ring strain we're going to have to deal with. And it turns out that the ring isn't flat in order to get around these sorts of issues, right? So if you look at the Newman projection, right? So if you look at one of the reasons why cyclopropane is terrible, right? You have terrible angle strain, right? But you also have, if you look at the Newman projection along one of these bonds, right? You have these eclipsing hydrogens, right? So this extra instability there. So this is really hard to make. It's really unstable. But cyclobutane, right? So if it was flat, right, it would be all of these. It would be similar to this, where the hydrogens would be eclipsing. So what it does is it torques itself a little bit and relieves that little bit of torsion strain that it provides, right, is more than compensated for the fact that now these hydrogens, when you rotate it, right, so if you make a 4-membered ring, hopefully you can make it with your model set, it'll twist slightly and you get these hydrogens out of the eclipse mode, right, so they're not quite eclipsed anymore. They're not staggered, but they're not feeling each other nearly as much as they were before. Okay, once you get to cyclopentane, what happens is, right, so now you've got, you're getting much better bond angles, right, but again, you have to deal with this eclipsing interaction here, right, so if it was flat, right, you would have these guys would be eclipsed, right, so what it does is it twists a little bit, and so now they're not quite as eclipsed as they were before, right? So it's not completely staggered, but it's not eclipsed. So it sort of puckers a little bit and puckers a little bit to relieve that steric strain. But when you get to the cyclohexane, now things become very pretty, because what will happen is now everything is staggered. If you look down these two, everything is staggered. Now you're going to have you're not going to really actually have much of that gauche interaction, right? Because you don't have, and I'll show you why. So when you go here, right, so you're looking down the bond angle, right? So what happens is, yes, you do have it, but notice the hydrogens are sticking out away from each other. They're not; these two guys aren't knocking in. You know, the hydrogen here and the hydrogen. You know, if it was, these two hydrogens wouldn't be knocking into each other. These hydrogens and these hydrogens are pointing away from each other, right? There's no hydrogens in the middle here, right, to be able to knock into it. So we don't have this gauche interaction here. Okay, so everything's perfectly eclipsed. Okay, and so that's why we don't have any, when it puckers, instead of being straight, where everything would be eclipsed, if it puckers, right, one side goes up, one side goes down, now we have everything staggered, and we don't have any sort of steric strain, we don't have torsional strain, and we don't have any angles. We don't have angle strain either. This is where it's naturally going to want to go. Look at that. So just as an accounting here, right? So remember, when we draw these things, remember we said heavy bonds are coming out at you. So that means this side. So this side here of the bond is drawn using heavy lines to indicate that yes, it's coming out at you. We could do dashed lines in the back, but it becomes a little bit difficult to see what's going on. So we use those as sort of regular lines. So we say, okay, that's in the plane, and this part of the cyclohexane is coming out at you, which is this here, down there. So this is where a model set can come into play. Okay, there's actually two different conformations, right? So you can actually have it like this, right? So again, it's out here, but the problem with this configuration, this is sometimes called the boat configuration because it kind of looks like a paper boat. Okay. The problem is these things are what are called flagpole hydra. So assuming these are hydrogens, right? So they're pointed when you get in the boat. What they do is they're pointed right next to each other. Now, if it's in this configuration, actually what will happen is it'll twist a little bit. So it's actually a twisted boat. So it provides some torsional strain to compensate for that steric strain. So like that. But again, it's not. There's still some strain involved, and so it really doesn't want to be in this configuration. Right. So again, everything's staggered, but you have this steric interaction here. So instead, what it does, is it instead wants to get into this configuration here, which they call the chair configuration here. Right. It looks kind of like a lazy boy chair. Right. So okay. Now. Okay, so axial and equatorial bonds. Okay, so we're in this configuration, right? So we have all these different hydrogens, right? But remember, we talked about the upper face and the lower face, right? So we're going to talk about each one of these hydrogens can be slightly different reacting wise. So the reactivity is going to be a little bit different. Okay, so a little bit counting, right? So if it's going up at you, right? So if you lay this down, if it's coming up or it's going straight down, right? This one, and this one, this one, and this one, they're going straight down. This one, and this one, they're going straight up. We call those the axial. Okay, just like if you had a globe, right? It would spin around its axis. The axis would go up and down. These guys here that are pointed out towards the outside, it's not completely outside. It's slightly up or slightly down. Those are called equatorial, right? They're just like the equator of a globe. Okay, so that's where. So how do we figure out what's what? Okay, So the easiest thing, okay, so if you draw the structure, so the easiest way to draw a cyclohexane is to actually start with the middle ones. Okay. Okay, and then put one up. Doesn't really matter which one's up. One side up, connect the dots. Put one side down, connect the dots. That's the easiest way to do it, at least that I've found. Are there prettier ways to do it? Probably, but this is the easiest way to do it. Okay, so what you want to do is the easiest thing to do is to figure out where the axial bonds are. It's the easiest one to see is this one here, right? So notice how these bonds here are pointed up. That means that points to where these other bonds are pointed. That's where the axial is pointing, right? So this is pointing up, so this means the axial is up. Okay, just like down here, this is the other easy one to see. So notice how these are pointed down. That means the axial is down, like that. Now you're going to have to work with me on these, right? So this one here is kind of pointed down, right? So the arrow is kind of, right, the bonds are kind of pointed down. So again, that means the axial's down. This one here, notice how these are kind of up, right? It sort of points up like that, so that means the axial is up. Right? Same thing with here, right? So these guys are pointed slightly up, so that means the axial is up. This one's pointed down like this, that means axial's down. Okay, so now we found it, right? So this is up, right? Up, down, up, up, down, up, down. That means, right, so we have to have on each one of these, we have to have an up and a down, right? So if the axial's up, that means the equatorial, which is going off to the side, that one's going down. So the equatorial is going down, right? So that means, so this one's going down. So that means the equatorial's, this axial, right, we said it's going down, right, because the bonds point down, the carbon-carbon bonds point down. So that means the equatorial, which is off to the side, is considered up in this case, right? That's down. Again, if the axial's up, that means that the equatorial is down. This one's down, so that means the equatorial is considered up. Axial's up, so that means the equatorial is down. And right here, axial's down, so that means the equatorial is up. Now, this one's the easiest to see up, down, do your best in here. It doesn't matter if you do it over here, right, here, or here. I'm sure there probably is somebody's going to come in and say, oh, there is, but for when you're learning, just do your best, right? The axial is the easiest one to find. If you can find the axial, that means you automatically know what's going on with the equatorial. Okay, find the axial because it's going to go the opposite way. It's going to go off to the side, but it's going to go the opposite way. If this is up, that means the axial is down. If this is the axial is down, that means the equatorial is up, right? So it means you only have to remember half the way and then you can figure out what the other one's doing. Okay, so we figured it out, right? It's axial equatorial, not too bad. Stuff like that. Okay. So the problem is, right? So if you take this, right? So this one's right. So here, let me swap this for a blue. Okay, so it's not frozen. What happens? Right. So this is right. So these guys here are pointed. Right. These guys here are pointed. These carbon-carbons are pointed down. Right. So that's axial. So that means equatorial is up. This one, the carbon-carbon bonds are pointed up, so that means axial is up. So the blue is axial, the red is equatorial. The problem is, right, so when we're moving around, well, what happens if I put it in this configuration, right? So what I've done is I've kept the middle ones where they were, but instead, I've moved this one up and this one down. This carbon I've moved down, this carbon I've moved up. Okay, so this is what's called a chair flip. It's a chair flip. Right? So so if your head was up here, right, now it's going to flip down to be down here. Okay? But remember, okay, so what's happened is, right, so now, you look at where the axial equatorials are. So for this one here, so we're looking at this, so we're looking at the blue one, right? Now the axial is up, right, because the carbon-carbon bonds pointed up, so axial up. So that means the equatorial is down. this one here, right? So now the carbon-carbon bonds point down, so that means axial is down. That means equatorial is up. Okay, so before, right? So, right, we had the down, equatorial down, and then we had the axial up. Oh, excuse me. Oops. What did we have before? We had it like this. Right, notice how the axial was up, right? So we had this, and then the equatorial down. Oh, excuse me, the equatorial up. So that's what we had before, right? When we do the chair flip, what's happened? Now the up is, it's not down, it's axial now. Okay, and now the up isn't axial anymore. Now the up is equatorial. Okay, so during a chair flip, axial becomes equatorial, and equatorial becomes axial. So chair flip. Okay, the ups are still, it's still in the up position relative to the to whatever is attached on the same carbon, right? It's still staying up, up, up. But what up is, the definition of what up is, changes with the chair flip, right? So here the blue is axial, right? It's still up. This is still up, right? So this would be, right? So this is the equatorial because the axial's down, right? The axial's up here, equatorial's down. But when we do a chair flip, it's still up, but now what's up is the axial, and what's, in this case, what's up in the blue is the equatorial. Like that. So chair flip, equatorial and axial come up, but ups stay up and downs stay down. Stuff like that. So okay, so now we have to configure. So why would it do this? Right? So when in doubt, it's all because of relieving strain. Stuff like that. Either be more reactive or to relieve strain. Okay. So remember when we were talking about Newman projections, right? We were talking about two groups clashing, right? So sterically clashing. Okay. So if you have this one right here, right? So if you have a methyl group, right, in the axial position, right? So if you have so if you have hydrogen here, right? So if you put a methyl group here, what's going to happen is these guys, assuming these two are hydrogens, right? These two are hydrogens. This methyl group's going to be close enough to interact with them, right? And that's actually going to be a steric hindrance. So there's going to be steric hindrance here and here. Okay, so there's steric. So how do we relieve it? We do a chair flip and move that there and move that there. Right now, it's just hydrogens pointing out here, right? So now this is pointed out. Now the methyl is equatorial, right? So like that. So now the methyl group's equatorial. Now there's no interactions. Okay, so we can do a chair flip to relieve strain. Okay, and if you look at table 4.1, there's a list of strain energies. I'm not going to make you memorize these. If I wanted to do it, then I would tell you, I would have you, I would give you the chart, right? But it's just like Newman projections, right? You just add up everything, right? So you're interested usually with what are axial and what are interacting with these other axial hydrogens. It's usually what it is, right? So in this case, right? So here's the other axial group here, right? So interacting here and here and here and here, but that's zero. These are small, so this is zero. But there is some steric energy here and here. Okay. Okay. So, right. So if you have another methyl group in here, right. So let's put another methyl group in here. Okay. So you still get the gauche interactions, right. So if you have trans, right. So this one's going up, right, because the axial is down. This one's axial is up, so this one's down, right. So this one's down, this one's up. So it's trans, right? Down, up. That's the definition of trans. Okay. So, but you can still get gauche interactions, right? So you can still have, right? So if you look at Newman projection right down there, right? So they're 60 degrees away from each other. You're still going to get gauche interactions. Okay, between this methyl group up here and that methyl group there. Okay, so that's going to be some ring strain. Okay, so hey, well, what do we do to get rid of ring strain? Let's do a chair flip. Oh, now here's the problem. Okay, so now not only is this methyl group interacting with these two hydrogens, right, but this methyl group is interacting with these two hydrogens, right? So even if you do a chair flip, it may not relieve the strain, right? So this one has, so each one of these is, was it 7.6? I think it is, something like that. No, it's something like that. 4 interactions, right? So that would be, so a little under 4, so like 3.8 or something like that. Like that, so something like that. That's why we have the chart. So anyways, so you still have some interactions, so this isn't 0, but it's a lot less than these interactions here. Okay, so with that, so you have to be careful with the chair flip. Usually what you want to do is you want to put the biggest group equatorial and take the pain, with moving things around. Okay. Okay, so what happens if you have, say this is cis, right? So now instead of being up down, I'm going to be up up. Okay, so what are we going to do now? Well, in this configuration, right, we still have, right, this is equatorial, so that's great. But here we have this red methyl interacting with these guys. So that's some strain. So hey, let's chair flip and see if we can get rid of that. Right? So move this guy. Right? So now we've moved this equatorial, yay, but now this one's axial, right? And you're interacting with these two methyl groups here. Okay, so even if you, right, so this methyl group interacts with the blue hydrogens, you do a chair flip, and you still have a methyl going here. So there's no preference between the two. It's still, right, it's still going to be this interaction here, right? So it's going to be between the two. It's going to keep constantly. It's going to spend an equal amount of time in each one. There's no preference. So, okay. So what if we have two, right? So now let's say we have something really big. Okay. So assume that this is okay. So okay, so now you say, okay, so we've got, there's cis, right, because it's one, let's see, make sure I get this right. There we go. There we go. Okay, so here's the chlorine. Here's this giant T-butyl group. So you go and you add them up. Okay, so in this position here, right, so it's cis, right, because it's up, up. Okay, so here's the chlorine, right? So you have the chlorine hydrogen interactions here, the axial, right? So each one of those is worth 1, but when you chair flip it, right? So now you've got T-butyl hydrogen interactions, right? Each one of those is worth 11, right? So what it's going to do is it's going to chair flip back. It's going to spend more time in this position, right? Because there's just simply less strain, right? It takes a hit. It's not 0. It'd love to be 0, but it's not. But it'd rather spend 2 kilocalories per mole of steric strain in this configuration than have to spend 22, 23 to be in this configuration. That's all that happens. Okay, so again, you have either one of these two conformations, right? You go look at the table, right, for cyanide hydrogen. You look at that. And you look at this is a phenyl. If it's just a benzene side chain, it's called a phenyl. Long story about that. It's not called a benzyl. It's called a phenyl. So now you put the phenyl in the axial position, right? So when you chair flip, this goes equatorial. This becomes axial now. Look at that. When you look up the interaction, so each one of these is worth 0.4. Each one of these is worth 6.3. Right. So, but notice. Right, so it's going to spend a lot more time in this configuration than this configuration because there's less steric strain. But notice, right, a phenyl group has 1, 2, 3, 4, 5, 6. Its configuration is each one of these is worth 6 kilojoules per mole. But these guys here, the T-butyl, which only has 1, 2, 3, 4 carbons, right, is each one of those is worth 11. Right, so even though it has 2 more carbons, right, it's smaller. It has less steric strain, and that has to do with the fact that the way this is built. So this is actually it's actually fairly flat. This one, it turns out, is flat, while the T-butyl group is wide, right? So when you're doing sterics, right, you're dealing with things that are big, right? right? Not just the number of hydrogen, not just the number of carbons, right? But how they're oriented in space. So this one here can actually orient itself in space and be much smaller, even though the T beta group has 2 less carbons. So one of the little quirks. Okay, so last thing, right? So we can have these rings fused. Okay, you don't just have to have one ring, right? Something like that. So the way you do this, right? So these are what are called polycyclic alkanes. Okay, so there's more than one cycle in these things fused together, right? So where they fuse together, so in this case it's carbon 1 and carbon 6. Okay, that's called the bridgehead. Okay, that's where the fusion forms. Okay, and usually when you count these, right, you just count up the total number of carbons. Okay, and then they have a special name, but you don't have to remember those. Okay, so 6 carbon, 10 carbons is a decalin, right? And this particular one has 2 what looks like 2 cyclohexanes in it. Okay, okay, but these things can actually be put together in slightly different ways, right? It depends on which one the hydrogens are, right? So if the hydrogens are on the same side, right? So like this. So imagine the cyclohexane coming off of here. You can have the hydrogens on the same side, right? So these guys here, this would be cis-decalin, and the ring would come out here, on here, right? And notice how sort of it folds together. Okay. The other way would be is if the hydrogens were trans. Okay. In this case, although actually it'd be this and this. It would actually be in the axial position. Okay, so it actually would come out here. So the trans decalin is actually much flatter, and the cis decalin is more curved. Okay, and where do we see this? We see this in the steroidal, right? So the generic steroid structure is actually this. So three 6-membered rings and a 5-membered ring, but they're all trans, right? So these are all trans configured. Okay, so you notice you look in here, up, down, up, and there'll be a down here, like that. So up, down, or it'll be down, up, all the way through. So it's nice and flat, right? So they all have this general structure, right? And there's just usually the functional groups that are hanging off of here and hanging off of up here, right? So testosterone, which is for use for cooperation and maleness, right? So it has these 2 functional groups here and here. Progesterone, which is involved in pregnancy in females, I believe. It actually has the same groups down here, testosterone, progesterone, but the group right here, right, instead of having alcohol, now you have a ketone. Okay, but if you keep that the same and then just reduce this down, right, now you have an anticonvulsant, something like that. So these small changes in here make a big difference, but they all have this general fused ring structure. Okay, now the other thing that we can do, and this will come up later, right? So you'll have what are called bridgeheads. Okay, I don't want to break my model kit here, but what will happen is you have a cyclohexane ring. Okay, so if you look at it from the top, instead of having 2 hydrogens off of these guys, what happens is there can sometimes be a carbon in the middle. Okay, or you can have multiple carbons in the middle. Okay, so if you're looking from the top, if you look from the side, it's going to look like this, and this is the bridge. Okay, between the 2, right? So this is the bridge between the two cycles, right? So it's called the bridgehead. Okay, we see this you'll have this in your pharmacy. You may have this in your medicine cabinet. You see this in nature. This is camphor, right? So So you have this bridgehead here, right? So 1 carbon bridgehead. So this one here was a no carbon bridgehead. This one had a single carbon inside of it, right? A 6-membered ring with a carbon in the middle, right? And then it has these functional groups here. And there's actually a sunscreen based off of camphor that's approved in the EU. I don't think it's approved in the US anymore, or I don't think it's been approved in the US yet. Stuff like that. So there we go. Cyclic alkanes.